here is our unit 8. That's lesson 21.1, theoretical and experimental probability. Okay, it's a quick lesson. It's just a one-day lesson. We're not going to spend 2 days on it. And so you've probably seen probability before. I know I taught it in 6th grade when I taught 6th grade. And I don't know if you've kind of seen it here and there in other classes in math, but it'll probably come back to you. Okay, so your learning goals are: I can calculate theoretical and experimental probabilities, and I can explain the difference between experimental and theoretical probability. So here's some vocabulary to get familiar with. Probability is just how likely an event is to occur. It is represented by a number. That number is going to be anywhere from 0 to 1, and usually it looks like a fraction. Okay, so an impossible event, okay, you wake up tomorrow with the ability to fly or turn invisible, has a probability of 0. 0. An event that is absolutely certain to happen, like you are enrolled in geometry, has a probability of 1. Okay, everything else falls in between 0 and 1. Theoretical probability is what is expected to happen. All right, so if you have a coin and you toss it, the theoretical probability that it lands on heads is 1/2. The theoretical probability that it lands on tails is 1/2. That's what is expected to happen. Whereas experimental probability, those are the results of an experiment. So if you take a coin and you flip it 10 times, 4 times it lands on heads, 6 times it lands on tails, well, now your experimental probabilities are not the same as the theoretical, okay, because experimental is actually what did happen. It's the results of doing an experiment. Trial, that just means a repetition of the experiment. Every time you flip the coin, that's a trial. Outcome, each possible result of the experiment. Okay, so outcomes could be it lands on heads or it lands on tails. There's not any other outcome besides those 2 options. An event is the set of the outcomes. A sample space is the set of all possible outcomes. Those last 2 we won't use too much, but I just threw them in there. But the trial and outcome, you'll see those words show up today. All right, so there's a formula to find theoretical probability. And since theoretical probability is a value, anywhere from 0 to 1, it can be represented as a fraction. And so the way you figure out that fraction, the numerator is just going to be the number of favorable outcomes. Okay, what is it that you're trying to get to happen? And the denominator is the total number of possible outcomes. All right, and then if you look at that value, that is your theoretical probability. There's an example for that right below where we have a wheel. And on this wheel, there's 8 different sections that are different colors. And so to find the probability of spinning yellow, since all those sections are the same size, and 3 of those sections are yellow, the number of ways to spin yellow is 3, and the number of possible outcomes is 8. So the probability of getting yellow is 3/8, which is a number between 0 and 1 as well. All proper fractions where the numerator is smaller than the denominator, that would have a value between 0 and 1. So that's how we usually represent our probabilities. We're going to do some examples. The first one, we're going to find the theoretical probability. In a classroom where 4 students have Fs, 7 students have Ds, 12 have Cs, 6 have Bs, 8 have As, what is the probability of randomly picking a student with an A? So we're just going to use this formula to find the theoretical probability. And one way of writing probability is with a capital P, that stands for probability, and then in parentheses you put the thing that you're trying to find the probability of. So I'm going to do that for you guys and show you that. right, so probability of, so I can just kind of make that shorter by putting capital P and then parentheses here, and then inside the thing that I'm trying to find the probability of is randomly picking a student with an A. All right, and that's going to be equal to, we're going to have a fraction here. And so in the numerator of our fraction, the number of favorable desired outcomes. So what I want to happen is to pick a student with an A. So what I have to figure out is how many students have A's. So the numerator is going to be the number of students with A's. And my denominator, the total number of possible outcomes is going to be the number, or the total number of students with grades. Okay? And so we just say with students, because if you're a student, you should have a grade. Great. And now I'm going to replace these words with numbers. So the total number of students with an A, just looking up at the word problem, you can see that there are 8 students that have A's. So the number that goes in the numerator is going to be an 8. And then I need to find the total number of students. Well, let's see, the 4 of them have F's, 7 have D's, 12 have C's, 6 have B's, and 8 have A's. So I'm going to have to actually add up all these values. So if I add 4, 7, 12, 6, and 8, I already have 7 responses on here. So I'm going to let somebody else do this calculation and see what you guys got. 37. 37. Good, 37. Awesome. So yeah, that's my denominator. And right here, so I would type 37. And so that's the probability of randomly picking a student with an A. 8 out of 37, which is a value between 0 and 1. Okay, so when you're doing probability, you should always have something, you know, it could be 0, it could be 1, or anything in between, but you're not going to have a number larger or negative or anything like that. So that's one way to check your work. You can always figure out, is your fraction a proper fraction where the numerator is smaller than the denominator? Then that is a value between 0 and 1 and you're good. So I'm going to leave it on student pace because I'm going to go to the next slide, but you might still be writing on that slide. Actually leave this here for a minute just so you can get caught up, and then we'll go to the next slide, which is another example of students and their grades. Okay, so slide 6. Another example of finding theoretical probability. And so exam grades of students in a history class are shown in the bar graph over here. So along the bottom, we have the letter grade, and then it shows us how many students have that grade for each letter grade. And the first thing we're going to do is find the probability that a randomly chosen student in the history class earned a C or better. Then we're going to find the probability that a randomly chosen student in the history class earned a C or lower. So the difference between this problem and the last problem is that we were just finding the probability of getting a single letter grade here. So we only had to consider just the number of students with an A here, but now I'm looking at a C or better. So how many students have a C, a B, or an A? A C or lower means how many students have a C, a D, or an F. And if you're typing, I know it kind of gets crowded, so you might want to change the size of how big you're typing. And so I have the probability of student with a, I'm going to do W/ for with a C or better. Be equal to So in the numerator, number of favorable outcomes, we want to know how many, the number of students with a C, B, or A. That would be divided by the number of total students . All right, so number of students with a C, a B, or an A. If you look at the bar graph, you can see here there's 8 with a C, 12 with a B, and 7 with an A. So I'm going to add these 3 numbers together. And then the total number of students, well, I need to add all the number of test grades together. So 3 plus 1 plus 8 plus 12 plus 7. And so these are the 2 calculations we need to figure out to get our probability here. And sometimes you can simplify this probability because it is a fraction. Sometimes you can't. So it's kind of looking at your guys' work and see who figured this value out here. 27 over 31, 27 over 31, 27 over 31 is correct. Oh, that's my, there we go. So right here we have 27. If I add 8, 12, and 7 together, you get 27. And if I add those numbers, which is 8 plus 12 plus 7 plus 1 plus 3, so 4 more, or 31. Okay, and now we're going to do the second part to this question, which is finding the probability that a randomly chosen student in the history class earned a C or lower. So sometimes when you do probabilities like this and you're asked to find 2 probabilities, maybe those 2 events are like, there's no overlap between them and you're covering all the cases. There's multiple ways to do your work here, but in this case, these 2 probabilities I'm being asked to find, there is an overlap. They're not exclusive events. So the first probability it's anyone who has a C, a B, or an A. Now, our second one is also including the number of students with a C. So there is an overlap between these two probabilities that we're finding. So I do have to actually work it out this way with the formula both times. Because if they were exclusive and I was covering all the bases, then I could just actually use subtraction. You can subtract from 1 because 1 is the absolute probability that something will happen. But in this case, we can't do that. But you're going to see we will be able to do that in a future example coming up. Okay, so probability, student with a C or lower. So a C, D, or F. And so our number of favorable outcomes is the number of students with a C, D, or F. And this is divided by the number of total students. Number of students with a C are 8. Number of students with a D are 1, and number with an F are 3. In the denominator, we've already added up the total number of students in the last question, so we could jump right to putting 31 in the denominator. And then if I simplify this, the numerator 8 plus 1 plus 3, we get 12 over 31. 12 over 31. Okay, so we found our 2 probabilities here. Okay, so I'm going to move on to the next slide with you guys. And this is just a summary slide about the difference between experimental and theoretical probability. So on the left, we have experimental probability. This is found by repeating an experiment and observing the outcomes. We have not seen this yet. On the right is theoretical probability, is what is expected to happen based on mathematics. This is what we have been doing. So the difference here is that when you're writing out your fractional values, the experimental probability of an event is actually based on the number of times it happens divided by the number of times you did the experiment, the number of trials. And then the theoretical probability is the probability of an event where you have the number of favorable outcomes, okay, what you want to happen divided by the total number of possible outcomes. Okay, and so these two probabilities you find, you might be talking about the same thing happening, like tossing a coin in this example here, but we clearly have two different probabilities on each side. So in the experimental probability, you take a coin, you toss it 10 times, a head is recorded 7 times, a tail 3 times. So the probability of a head here is 7 out of 10. Probability of a tail is 3 out of 10. Whereas the theoretical, what you expect to happen, a coin is tossed, the probability of head is 1 out of 2 because there's one side of the coin that has a head, there's 2 sides to a coin. Probability of a tail, 1 out of 2. Same thing, one side has a tail, 2 sides to a coin, 1/2. So these could be different depending on if it's an experiment or theoretical. Sometimes they're the same. The more you experiment with something, the closer and closer you're going to get to theoretical probability. And so we're going to do an activity tomorrow where we will be flipping a coin and doing whatever else we want to kind of do some experimental probability and see what we get. This next question example we're going to do is an experimental probability one. Okay, so this is an example where we find the experimental probability. The probability of an event is equal to the number of times the event occurs, it actually happened, divided by the total number of trials. How many times did you do this experiment? So this case is a water bottle is flipped 24 times. 21 times it falls over on the landing. 3 times it lands standing up. Find the probability that the water bottle will fall over when tossed. Find the probability that the water bottle will land standing up when tossed. So we're finding our probabilities based on this experiment here. Then capital P is how you can represent probability. And then use parentheses and fill in what it is you're trying to find. Okay, probability bottle falls over. This is going to be the probability, number of times it occurs. So how many times did it fall over? It says 21 times it fell over. Number of times it falls over, that's divided by the number of tosses. And then you're just filling in those parts of the fraction with the actual numbers from the experiment. So 21 over 24. The other ones we've been looking at, we weren't able to simplify this fraction. 21 over 24 is simplifiable because there's a GCF of 3. So I can divide 3 out of the numerator and the denominator. And get a simplified fraction of 7 over 8. And then finding the probability, the experimental probability that the water bottle will land standing up. have the number of times it lands standing divided by the number of tosses. It's just based on the experiment. We're looking at that. So that's 3 divided by 24 this time. And again, this is a fraction that we can simplify. GCF of 3 gives us 1/8. Okay. Now, this is kind of a special situation with these two probabilities that we're finding. So if I toss a bottle, I expect one of two things to happen. It's either going to fall over or it's going to stand up. And so because when I toss a bottle, one of these two things has to happen, if I was to add these two probabilities together, it should equal 1. And that is one way to check your work on these types of problems. It's also a way to find the other probability in a different method. So these two events are exclusive. There's no overlap between what we're talking about. So their probabilities should add to 1 in this case, and it covers all the possibilities. So 7/8 plus 1/8 is equal to 8/8, which is equal to 1. So, when you're thinking about a situation, once you find one of these, I could have found this other probability by doing 1 minus 7/8 also. It would have worked out the same. But this is a good way to check your work when you're covering all the possibilities, and these two events, or the events that you're looking at, they do not overlap. So these two events are exclusive, and we covered all the outcomes, which there's only 2. Falls over, it stands. Right, so at this point, there are 2 slides left. Okay, and those are your ones that you're going to do on your own. The first one is a theoretical probability question about a deck of cards. Okay, so you have a standard deck of playing cards. A standard deck, this is what it looks like. There are 4 suits. We have hearts, spades, clubs, and diamonds. Each suit has 13 cards. What is the probability of drawing a spade randomly out of a full deck of cards? So you have your formula here for theoretical probability. You have a picture here of what a full deck of cards looks like, and you're going to find this probability here. And then the last question is, can you explain to me the difference between experimental and theoretical probability? So basically, that's the I can statement. Can you do that? I'm going to leave my screen right here, and that's it for the lesson. Now, over the last 3 days, Monday and Tuesday, we did MDTP.